So we have a problem here that says that we have a young woman standing on a swing, and she's spinning at a rate of 1 rotation per second. Her arms are initially straight out from her body, but then she tucks them into herself, changing her rotating speed. She is 60 kilograms altogether, but her arms are 7 kilograms separately. And then we have this first part that is asking, using the diagrams and assuming that the swing is negligible, use only variables to equate the initial and final states of angular momentum. So when we think about angular momentum, we have two types that we focus on. We focus on the translational angular momentum, and we focus on the rotational angular momentum. And we have this woman standing on the swing, spinning at a rate of 1 rotation per second, but she is not translating at all. She's not moving. The swing's not moving. So what we're just going to be looking at is the evolution of this rotational angular momentum that this woman has. So obviously, based on this diagram, we have an initial state of angular momentum and we have a final state of angular momentum. And so we want to look at the rotational angular momentum of these two states. And we are going to write both of these out in full variables so that we can see how this angular momentum progresses. So since we're going to be working with rotational angular momentum, we might as well have the equation for it, and that would be the moment of inertia of our object, whichever one we're looking at, times our angular velocity. And we might as well write out the translational angular momentum as well, which is just mass times velocity times the radius of rotation. But anyways, we're just going to be using this equation down here for rotational angular momentum. And what we want to do is look at our diagrams once again, and we can see also based on what we've been given here, we have the moment of inertia of a rod given to us and the moment of inertia of a cylinder given to us. So we have in this initial state a cylinder and a rod both rotating, which would represent the woman herself, her body, and then her arms sticking out. And then in the final state, we just have a cylinder. So her arms have been brought into her body, and that's just it for her final state. So we have essentially the angular momentum of our initial state being the rotational angular momentum of our rod, or her arms, plus the angular momentum of the cylinder, or her body, and then that's just the initial state. We have the final state being the angular momentum of just the cylinder for the final state. So we have to write all of these in their specific variables. So the angular momentum in terms of her arms, her body, and then just the arms and the body together. And we know that all of these three angular momentums are going to be the moment of inertia times the angular velocity, so we can just flesh out these moment of inertias automatically. So these are going to be the angular momentum of a rod, which will be the moment of inertia of a rod, which is 1/12 times the mass of her arms times the length of her arms squared. And then this is times the initial angular velocity, and then we're going to add the angular momentum of the body in the initial state, which would be the moment of inertia of a cylinder 1/2 times the mass of her body without her arms, and that'll be important later. but without her arms, because her arms are being counted as a separate angular momentum. But this is times the radius of her body squared. And then this will all be equal to, this was all just the initial state. Oh, we forgot, times the angular velocity, the initial angular velocity of this initial state. And these are actually the same initial velocities. But anyways, this is all going to be equal to the final state, which is all one big cylinder. So this is the moment of inertia of a cylinder, 1/2 times the mass of her body plus her arms, because now she's brought in these arms and they're being added as one huge mass. So, and then this is multiplied by the radius of her body once again. We're most likely going to assume that her radius of her body hasn't changed. And then this is all times the final angular velocity, because as she brings her arms in, the problem said that her rotating speed will change after she tucks them in. So this huge equation is the initial and final states added together. And as we can see, it gets pretty complicated even just with 2 objects in our system in the initial state, and then going into 1. So with that, we can move on to the next part.